everyone. I'm Dr. Isha Mehra from ABES Engineering College. In my today's presentation, I'm going to talk about the optical fiber, types of optical fiber, and losses involved in optical fiber. In my last presentation, that is part 4, I talked about the basics of optical fiber, principle involved in optical fiber, then numerical aperture, acceptance angle, and acceptance cone. So the outline of this presentation is what is fractional index change. We also call it FRI, fractional refractive index. Types of fiber. There are various kind of fiber which I'm going to describe. Then losses involved in fiber like dispersion, attenuation. Then applications of optical fiber. So initially, I'm going to start with fractional refractive index, which is also a part of the numerical aperture and acceptance angle. So what is fractional refractive index or fractional index change? This is represented by this symbol. It is basically the ratio of the difference between core and cladding refractive index to the refractive index of core. N1 is refractive index of core and N2 is refractive index of cladding. Refractive index of core and refractive index of cladding. As I have already explained in my previous presentation that N1 should always be greater than N2, then only TIR can happen or TIR is possible. So there is a relation between numerical aperture, I call it NA, and this fractional refractive index change. So we can write numerical aperture as I have already derived it in my last presentation, N1 square minus N2 square. We can further rewrite it as N1 plus N2 and N1 minus N2. So numerical aperture in this case will be N1 plus N2 and it will be written as N1 into this fractional refractive index. From this equation number 1, we can say. So this is only possible if N1 is nearly equals to N2. Now in this case, numerical aperture will be given as under root of N1 plus N2 by 2, 2 into N1 fractional refractive index. This is equals to 2N1 square fractional refractive index, and A is equals to N1 under root of 2 of this change, fractional refractive index change. So this is very important formula. Now, it is also related to acceptance angle, as we already know that numerical aperture is the sign of the acceptance angle. Now coming to our next topic, that is types of optical fiber. Now this optical fiber is classified under 2 categories on the basis of modes, on the basis of refractive index profile. Refractive index profile. On the basis of modes, from the name we can say that this optical fiber is classified under 2 categories. One is single mode optical fiber and other one is multi-mode optical fiber. From the name, we can easily say that single mode optical fiber, only one mode propagates through this optical fiber, like this. While in multi-mode optical fiber, multiple modes travel through this optical fiber. like this, and so on. So from the name, we can easily see the number of modes from this part. So let me explain this in brief. On the basis of modes, if I'm going to differentiate between the single mode and multi-mode optical fiber, there are a lot of differences. The first difference from the name, it is clear. Only single mode propagates through it. In multi-mode, only, in fact, many modes travel through this. So we can say many modes or large number of modes travel or propagate through optical fiber. Now, as we say that only one mode propagates, this means the core diameter is very small because it's not required over here. Right, it's a very large diameter, it's not required over here. So in this case, the diameter of core is of the order of 5 to 10 micrometer, and diameter of cladding is of the order of 125 micrometer. While in case of multimode optical fiber, diameter of core diameter is of the order of 50 micrometer to 100 micrometer, because in this case large number of modes travel. So diameter of the core should be large, and in case of cladding, it can be, the range can be 125 micrometer to 500 micrometer. Now, in single mode, again, as the core size is small, so definitely the numerical aperture, acceptance angle, all these parameters will be small. And acceptance angle, we can say, so these will be small, very small. On the other part, if we say about multimode optical fiber, then numerical aperture, acceptance angle, all these parameters will be large. And acceptance angle will be large. Then coming to the next point, there are many points. Modal dispersion does not occur in single mode optical fiber. Modal dispersion, which happens due to large number of modes, it does not happen. It's not possible in single mode optical fiber. While in case of this, modal dispersion is dominant because of large number of modes. Last but not the least, we have to draw a diagram for this. So it will be very clear from the diagram that only single mode is propagating through it. That's why the core size is very small. While in this case, if we talk about the multimode optical fiber, it will be like this. Then in this case, large number of modes, they travel through the optical fiber like this. Large number of modes can travel through the optical fiber. So this is the multimode optical fiber. Now the multimode optical fiber is also further classified under different categories, that is step index optical fiber and graded index optical fiber. So why it is required? What is the basic need of this? If we have single mode and multi-mode optical fiber, then what is the requirement of step index and graded index optical fiber? So from the diagram, it will be very clear, and from the refractive index of profile, also it will be very clear. Now, both are the cases of multimode optical fiber. So in step index optical fiber, what is happening? The core N1 is constant. That is, the refractive index of core is constant. And definitely the refractive index of cladding is also constant. So if we draw a diagram for the refractive index profile, it will be like this. If this is the axis, so it will be like this. So if we say that the radius of the core is A and the cladding is B, if this is radius R, so the refractive index is varying like this. We can see this is constant throughout. The core part is completely N1, N1, N1. It's not changing. In case of graded index profile, we can see if we draw it like this. Again, this is radius. This is again plus A. This is minus A. We can see this N is changing with R. So this is the refractive index profile. This is minus B and this is plus B. So the cladding is constant. It's N2, N2, N2 throughout. But it's not completely N1. It's varying. Refractive index, it's maximum at the center, and as we are gradually decreasing toward the boundaries, it is decreasing. So if we talk about the step index optical fiber, let me write it again. And graded index optical fiber. So the very important point of these two is in step index optical fiber, all the modes will reach the output at different times. Why? Because the refractive index of core is constant. So if we have an equation V is equals to C by mu. So just let me explain this. If mu is constant, C is constant, so V will be constant. So the modes which are traveling along the axis, they will reach the output faster. And those who are taking a long path, they will reach the output slower. So these two modes, they are going to reach the output at different times, which is going to produce dispersion, which is going to produce the loss. But in case of graded index optical fiber, V is equals to C by N, which is changing with R. So if the center one, definitely, as I told, that the center one, N at center, is larger. So if it's larger, this means that the velocity will be slower. If velocity will be slower at the center, it will take time to reach the output. So different modes, they are going to reach the output at different times. This is going to minimize the dispersion. So there are few differences. The first part in step index optical fiber is refractive index of core is constant. In both cases, refractive index of cladding is constant, so I'm not mentioning it over here. While in case of graded, refractive index of core is not constant, it is maximum at center, and it gradually decreases. It gradually decreases as we move towards core cladding boundary or core cladding interface. There are few other points also, like the propagating rays reflect abruptly from the core cladding boundary. While it's not the case with graded index optical fiber, the propagating rays bend smoothly as they approach the cladding. As they approach interface or cladding. There are few other points. It has higher attenuation, as I already told. I'm going to explain it again. It is having higher attenuation factor, while in this case, it will be lower attenuation. It is going to have high numerical aperture, while it is going to have small numerical aperture. So why lower attenuation? There must be some confusion with the students that why it is lower attenuation. So this part will be based on this V is equals to C by mu. As I already told that if velocity will be constant, then all the modes they are going to reach the output at different times. There will be loss, there will be dispersion. If n is going to vary, then all the modes they will reach the output at the same time. So this is the difference between the step index optical fiber and graded index optical fiber. Now I'm going to talk about the losses involved in the optical fiber. So there are various losses involved in the optical fiber. So we can say attenuation. It's another name of loss, attenuation or loss of power in optical fiber. So the reduction in amplitude or power or intensity, any of these, the reduction in amplitude and intensity of a signal as it is guided through the optical fiber is called attenuation. So attenuation factor is given by minus 10 upon L log base 10 power output upon power input, and its unit is decibel per kilometer. So we have to take the unit for the optical fiber length is in kilometers. So there are three reasons for attenuation, for this loss. Why this is happening, why this loss is occurring. One is absorption, another one is scattering, and the last one is bending loss. So what is absorption? Why it is happening? Why scattering is there? What is this bending loss? So in absorption, absorption of light occurs due to imperfections. If there will be any imperfection in the fiber, definitely the light is going to get absorbed, it will going to hamper TIR, and there will be loss. So it is because of the imperfections of the atomic structure. What are these imperfections? Like OH minus, hydroxyl ions, or cluster of atoms. There are many reasons of this. Cluster of atoms which can absorb light. Definitely scattering. Scattering is also a wavelength dependent loss. This is basically a wavelength dependent loss. This occurs inside the fibers such as glass if we are going to use. So this happens inside the fiber. Since the glass is used in the fabrication of fibers, so the uneven structures, the non-uniform structures of the glass will vary the refractive index of the fiber. As a result, some portion of the light will be scattered. So in this case, if we talk about the loss, then scattering loss will be proportional to 1 upon lambda raised to the power 4. Bending loss, I'm going to explain in the next slide. So bending loss occurs because of the bend in the optical fiber. Now it can be at a micro level, it can be at a macro level. So we can say macroscopic bending or micro bending. So microscopic bending is very small. Microscopic bending means there is very small bend at the core cladding interface. So it will look like this. It's a small bend, but this small bend can hamper the TIR of the system. So the light which is going like this, and it should be propagating, it should go TIR, but it is going to scatter here and there, it's going to escape because of the micro bends. That is tiny bends or curves that happen in the radius of curvature of the axis. So definitely it is going to hamper the TIR process. And if we are going to talk about macroscopic bending, so in this is basically a bending at large scale. Large scale. In this case, the diagram will be like this. We can see the ray which is coming from this side. Suddenly, this radius is such a large radius that again the ray can escape. So if the radius of the core is large compared to fiber diameter, it may cause large curvature. This results in decrease in network performances or complete signal failure. So that is why it is called as macroscope bending. There's another kind of loss which we called as dispersion, and dispersion means signal broadening or pulse broadening. Signal broadening or pulse broadening. Now this can be of different types like intermodal or intramodal. So what are the different parameters? So what are the different okay. So dispersion. We were talking about dispersion, signal broadening, intramodal or intermodal dispersion. So when we talk about this kind of dispersion, then what are the factors which are getting late? What are the factors which are not reaching the output at the same time? So if we talk about modal or intermodal dispersion, then different modes, they are going to reach the output at different times in case of modal or intermodal dispersion. So if we talk about modal or intermodal dispersion, in this case, different modes, they are going to reach the output at different times like this. This is modal dispersion. In intermodal or intramodal, the first one is modal or intermodal dispersion. In intramodal dispersion, basically different wavelengths. So we can draw it over here. Different wavelengths means suppose I'm going to incident the white light. So white light is going to have different lambdas like this. So these all wavelengths, they are going to reach the output at different times. We can see like this. So this is intramodal dispersion. Initially, the mode is same. The mode is a white light. But white light is having different wavelengths, as we all know. So they are going to reach the output at different times. And the last one is waveguide dispersion. So waveguide dispersion, what is the difference between intermodal modal and waveguide dispersion? So we can have a quick look over here. If we have, I'm going to draw here both the cladding and core. So there is very small amount of information which is also going through cladding. Now the refractive index of cladding is less as compared to refractive index of core. So the cladding ray will be faster. The information which is traveling through this cladding part will be faster. Why? Because again, V is equals to C by mu. This mu is less, so V will be large. Similarly, the information through core will not be so much faster as compared to the cladding part. So, information will be slower. Again, these two information, they are not going to reach the output at the same time. So, there will be dispersion, there will be pulse broadening. So, pulse broadening, we can have a look here on the upper side that if it input signal is like this, the output signal will be broadened. There will be difference in their intensities, and definitely this broadening is given by dispersion, or it is defined by dispersion. So this is what is all about this optical fiber. So I have almost covered all topics like attenuation, dispersion, then losses. These are all the losses which I have explained. Then types of optical fiber I have covered. These are the references. Thank you for your patience listening.